So it's an honor to be here with you today for this inaugural Voxxed Days Microservices in Paris, particularly on a topic that's equal parts exciting and frustrating. So I don't know how many times I've lost count that I can't feel like doing this anymore. I don't know if any of you have felt this frustration on a regular basis. I know I have. And often too many times to count, but that is the life we're in right now, unfortunately. So often feeling frustrated without seeing the light at the end of the tunnel. That is the joy that is microservices today. So right now, lots of enterprises are on a path to microservices, hurtling at full speed to implement them as soon as they can, and ideally, yesterday or last week. But as Patrick asked here, does everything need to be a microservice? And I certainly know I don't need mayonnaise as a service. So it's worth taking a moment to think about and reflect on the history of microservices, to see where we got to here, and to help us better understand any parallels and learning that has come before that we may not necessarily be aware of, that'll help us to develop microservices for the future. But firstly, who am I? So my name is Ken Finnigan, as Antonio said, and I live south of Boston in the US, working on microservice-related technologies for Red Hat, although as of last night, it's Red Hat, a division of IBM. So I'll need a new shirt at some point. So that includes leading the Thorntail and the Small Rye projects, which you may or may not have heard of. So for those that aren't quite familiar yet, Thorntail is the new name for Wildfly Swarm. That one might be more familiar. And I'm also involved in defining the specifications for Eclipse microprofile as part of my work on Thorntail. So I'll be speaking about those in more detail in a couple of talks I have tomorrow. So please come and attend those sessions. And also, come and say hi during the course of the next 2 days. It's always great meeting new people, and also to see in person people I've only known digitally before. So, let's get back to the topic at hand and begin our journey down amnesia lane. So though the term microservices might only be 6 or 7 years old, what it refers to is most definitely not. For many decades, we've had similar systems. So whether it was microservices, or fine-grained SOA, or enterprise service bus, Ginny, or even Corba, they all have something in common. They're all types of distributed systems. But before distributed systems, and yes, that was just a little bit before my time, everything was much simpler. There were no multiple processors on a system, no multiprocessor or multi-core hardware, entirely single process computing. In addition to single process, it was mostly single threaded, making mainframes the first digital timeshares in existence. So at that time, programming was done on punch cards, which I know I didn't have to grow up using. I know my father did. I don't know if there's anyone in the audience that's used punch cards before. Okay, maybe a couple of hands. No one really wants to admit that. So back in those days, you make a small mistake and you find you're re-punching a whole other stack of cards, or maybe making a patch of some kind. So, and the other thing with punch cards, I think it was the one time in history where probably the highest sale of rubber bands, just to keep those stacks of hundreds of cards together, because if you drop those, you did not want to spend hours reorganizing them and making sure they were in the right place. So, obviously this is an example of a patch on a punch card. And if only doing patches was as simple back then as it is today. Granted, you had to find the right hole to patch, otherwise you could end up creating more problems, but that's kind of what we do in software, make more problems. And no one said software development was going to be easy. So in the late 60s, we started seeing the use of client-server architectures, enabling the separation of tasks between requesters of a service and the providers of a service. And I must admit that when I put this slide together, I didn't intend it, but it's kind of an interesting coincidence, is I have an IBM server over here with a red shell on it. I swear I knew nothing about the acquisition. So that kind of architecture might sound familiar, and it should, because it's a distributed system. Client-server architecture is just another type of distributed system. So such a client-server architecture might not be what we picture first in our heads today when we think of distributed systems. We're likely thinking more something like this. But client-server architecture, though it's not a Netflix and doesn't have hundreds or thousands of services, it nevertheless distributes the processing of a single system across multiple systems. But there's a whole gamut of systems or applications we may not realize are distributed systems, such as web applications, games. Now, I must confess, I don't think Pac-Man is a distributed system, but it's just the best example of showing a game that I could find. In addition to games, there's obviously mobile applications and ATMs. Now that one was kind of interesting for me because about 10 to 15 years ago, I was working as an enterprise architect for Lloyd's TSB in London, and I was involved with planning and architecting the merger of Lloyd's TSB with Halifax at the time. So that was a 35 million customer account migration. And as part of that, we had to figure out how the ATMs were going to work during the cutover period. And at the time, having previously done mostly WAR, EAR developments on Java application servers, it never really dawned on me, and I didn't really have the history of distributed systems that I do today. But thinking back, it was like learning about how the ATMs store an event register of all the actions that have happened in a day, and only at the end of the day, some other process takes those event registers and then figures out what the actual balance for each of the customers is. That's another distributed system. So how tasks can be distributed certainly varies. In the beginning, clients were not very powerful, often being just a single terminal. So that meant all the processing that needed to occur had to happen on the server side. And over time, clients became more powerful, facilitating the move to what we call fat clients within client-server architecture. So that enabled us to reduce the network traffic going between the client and server to improve the overall performance of the applications. And an alternative to that would be multiplexing connections to reduce latency, and that's particularly beneficial for edge computing cases. It's all about determining the best trade-offs for your application. So if the networks are slow, move tasks to the client. With more and more tasks being distributed, we can't ignore potential issues with that distribution. So latency. A network's latency is one of the biggest problems faced by distributed systems, mostly because it's something we often don't think about and don't realize could be a problem. Because how many of you are actually actively monitoring your networks for latency? Oh, 2 hands. To be honest, I'm kind of surprised there's 2 hands. But it's one of the biggest problems we face. And it's almost, you could say, the silent killer of microservices. And if you don't monitor it, you're going to end up in a situation where you get hit with other problems that you'll think is something else, but it could easily be traced back to latency. So failures. I know I'm not crossing that chasm. Failures happen. We know they happen. but we don't always know how or when they're going to happen. So we can only anticipate some level of failure in our services and where it might happen. For the rest of the time, we need to learn from the experiences we have of our services in production to better ensure our failures reduce over time. We can't expect to be perfect in determining our failures when we're creating these services, just because they could end up behaving in ways that we don't anticipate. Bottlenecks. Can we really process all the requests before a given time frame? Often, our services aren't built to handle thousands and thousands and thousands of requests hitting us at the same time, particularly if they involve a high level of computation or slow or blocking tasks that just make it perform badly. So all these resiliency issues have occurred in the past, and they continue to occur today. But we must do our best to prepare for them and counteract them. So for a client server, an example of that is adding retry logic into the client for basic failures and timeout handling to communicate with the server. So this is where RPC became a foundational backbone of most early distributed systems. But once we had object-oriented programming, and it was the rage in the late 80s, we needed a way to utilize that model in distributed systems. So that led us to the early 90s, where along came everyone's friend, Corba. Now, before I go too much further, I know there were a lot of hands earlier raised when Antonio mentioned Corba. Is there anyone still using Corba today? I hope I didn't see that hand over there. I'll just pretend I didn't. We hammer Corba pretty hard these days, but you could argue, maybe at a bit of a stretch, that Corba is a form of Kubernetes, but without the containers. And if you just replace YAML with IDL, it's kind of a scary thought, but I had it the other night, and it's not too far from being the truth, that they're doing very similar things, just in slightly different ways. So in 2002, Java Enterprise Best Practices came out and had the following things to say about remote method invocation. It suggested retries for handling network failures, providing a unique request ID to prevent the server reprocessing requests that had already happened, but the client had failed to get the response. Wrapping RMI calls into objects to support reuse and the separation of business logic. Logical naming of services to make them easy to find and look up. And also caching, so that if we've made a request across to a server, if it's something that isn't going to change, no matter how many requests we get, then we cache it and return that every time to speed up the response. All those things that were defined as recommendations for RMI in 2002 are incorporated into the Netflix libraries. As always, everything that's old is new again. So in 2003, Kephart and Chess discussed the lifecycle of autonomic components. In addition to monitoring themselves, they postulated that they continually monitor their suppliers' and consumers' level of service to ensure that they are not exceeded. Essentially describing how Netflix Hystrix monitors and restricts the number of requests it can process, as well as the number of threads it uses when communicating with external services. So through the early to late 2000s, we saw application logic for resiliency being extracted into application services and ESBs and SOAs for reuse amongst all applications within that middleware. During this period, we saw the rise of SOAP protocols as a way to communicate between these distributed systems, along with WSDL and UDDI. Unfortunately, all this never really lived up to the hype and promise at the time, especially with regards to UDDI. So within the last decade, we experienced the explosion of distributed systems libraries in the wake of Netflix open sourcing their internal code, such as Ribbon and Hystrix. It was during this period that microservices became the hottest buzzword in the industry, and since the opening of those Netflix libraries, we've seen more libraries for handling distributed systems, such as Spring Cloud, which has another number of libraries as well. And then in the last year or so, we've begun to see a shift of latency, fault tolerance, bottleneck handling being shifted back into the environment, which in this case right now is service mesh, with Istio being the biggest example of that right now. So will service mesh help us solve these problems? Well, I'm happy to say yes, that they will, but some of the same problems they'll solve are the ones we've had 20 or 30 years ago. And along with that, they'll introduce some new ones that we thought were already solved. So software development philosophies and practices can be somewhat cyclical, falling in and out of favor as we evolve through the years. The same cycle happens with distributed systems. We begin by embedding all the resiliency handling into our application code itself. And then we take the step of moving them into reusable libraries so that other applications can use them as well. And then we further externalize that into our middleware so that any application deployed on the same middleware can access those features. And then we come full circle and round to moving them into the environment, which is what we're going through right now. And then at some point, we usually get back to the saying of having everything in the environment is too complicated, I want it all back in my application, and we go back around the loop again. So we've gone around the loop a few times over the last 2 or 3 decades or 4 decades in relation to distributed systems. There might be some improvements in each of those steps. Things get better and we do things different in the past. But in essence, the theory behind all these things hasn't changed. We're solving the same problems that have already been solved before. So that means that we're not really doing anything revolutionary, it's barely evolutionary. And in terms of software overall, that's something that needs to change. So we all understand Jonah's thrill and excitement from inventing new software. That's what software engineering as a profession is all about, building and inventing. Now granted, sometimes that can be a bit problematic because we end up with the concern around not invented here syndrome. It's something we all fall prey to, but it's something we need to try and get better at. So I'm posing a challenge to all of you, myself, and anyone else in the industry to solve problems that haven't already been solved. We need to stop reinventing the same wheel just because we can. Now, I don't know about you, but I don't think we need the 250th JavaScript framework to set a style on a DOM element. Now, that might be a bit exaggerated, and it's not just JavaScript that does this. We do it in Java as well. But we need to get better at inventing things that haven't been solved before. And I know from personal experience, it's very hard when you own that code to let it go and merge it into something else. But it's like, I want you to think about if there were 5 different people around the world who came up with a similar idea to solve a particular problem. They could all go away and solve that problem. Now, although the implementations between them might be a little bit different, I would say that there's a good chance that 60 to 80% of that design is going to be fairly common across all 5 of them because they're trying to solve the same problem. Now in that situation, it would be much better for all of them to come together and agree on what they're doing to come up with a common way to solve that problem rather than 5 different ways. Both from a more effort onto a single problem, but also from a user perspective, it makes it a lot easier when there's only 1 or 2 things to choose from and to evaluate than 20 or 30. We are spoiled for choice in software, and that often makes it very difficult to pick the right thing to use. So one of the most pressing challenges with microservices, especially with the rise of reactive programming and asynchronous processing, is the problem of quiescent state when updating microservices. So for those that aren't familiar, quiescent state is defined by Kramer and McGee. So in 1990, they postulated that it should be possible to modify a running system without stopping it entirely. This requires that nodes be in a quiescent state, which means that they're not accepting any communication either from external systems or from other nodes within the same system. So it's essentially like they've become siloed and they're not interacting, but they're still active. In this state, you can then perform updates to configuration and the like. Now, Kubernetes comes close to some of this in the sense of it starts a new instance because it's immutable and changes the config and gets it going. The problem, though, is that Kubernetes is only managing whether it thinks something is alive or not, and whether you've actually changed configuration. It's not monitoring whether there's any TCP traffic going into that node still, and it's certainly not aware if there's any asynchronous processing happening inside that node that it should let continue before killing that pod. So that's a problem that needs to be solved, because without solving that problem, we end up with our systems becoming in an inconsistent state. So, on a final note, some of you may have heard, and thanks to Antonio for mentioning, that I've recently finished writing and had published an Enterprise Java Microservices book. So it's now in print. I would have had more copies here myself, but they arrived on my home doorstep last week while I was at Code One. So for the conference, we've got about 15 or 20 copies, I think, Antonio, to give away, something like that. So, and I'd also be happy to sign them if anyone feels like my signature's worth anything. But I'm going to have some fun with it. So the first people to take a picture with me and tweet it to Manning Books, at Manning Books, will get a copy. Obviously, don't rush up on stage right now. Wait until after the keynotes or during today to come find me and make that happen. And don't be scared. I'm also tweeting as Manning Books today and tomorrow. They've let me take over their account, which was very nice of them. We'll see what damage I can do with that. So lastly, thanks for listening and enjoy the rest of the conference.